Okay. All right, now, we were ending with black robes and white robes in the Arabian Peninsula. What do we call the robes anyway?
Abaya.
For the girls or the guys?
For the guys. Can I write it on the board? What's it called? And how do you spell it for guys?
Kendura.
Males. What's it called?
K-A-A-N-D-O.
K-A.
K-A-N-M-D. No. One
Oh my
N.
god. Green.
I said it.
A-M-D-O.
How do you spell it?
K-A-N.
K-A-N-D.
D. O.
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 R-A.
Kendura.
Yeah.
And what's the females?
Abaya.
Green.
Abaya. A. B. A. Y. A.
Abaya. So, why are women's... I don't even want to go there. Anyway. Why are women's black and men's are white? Is there a
Colors.
fashion?
So like women are covered, you know? I think.
Whatever, I don't want to go there. But anyway, the Kendura is white, and it maintains the integrity of the body temperature.
So you can get white, yellow, black.
You get all different colors. We call that, right, we call that fashion, but that's okay. Anyway, if you're injured and you're maybe suffering from shock, whatever, and you don't want to lose any more energy, what they do is they put a silver blanket on you. Now, silver is the ultimate white, where it's not a question of white, it's a question of the better the surface reflects light, the more it maintains thermal integrity. So don't think it's white, think reflection. So mirror material, for instance, aluminum foil, will maintain integrity, thermal integrity. Okay, so let's have would you come up here and bring your paper, like don't go on camera, right here, and you can read that convection. You can read all three definitions. Come right here, okay?
I have the conduction.
Conduction's easy, that's just touching
Direct
and
contact.
contact. I like that, okay. So she's gonna read, Brianda's gonna read a book definition and see if it makes sense relative to what we explained. Go ahead, what are you gonna do first?
Conduction.
Well, you mean convection.
Convection.
Okay, you're gonna do convection first. Nice and loud for the folks back home. What do we got?
The transfer of heat by the circulation of or movement of the heated parts of a liquid or gas.
For instance, we're heating, or we can take heat away. It's heat transfer, right? So air conditioning, the circulation of the air in a room. A convection oven, you get the circulation of air. Yes? So read it again, the convection.
The transfer of heat by the circulation or movement of the heated parts of a liquid or gas.
Okay, and we could just put in there heated or cooled parts of the gas, liquid or gas, right? Because AC is also a transfer of energy. And radiation, go ahead.
The complete process in which energy is emitted by one body and absorbed by another.
Right, it's like the sun. Very good, thank you. It's emitted by the sun and absorbed by Earth. It's emitted by the sun and absorbed by Earth. Let's talk about how that might work. We have a question, Mohammed.
Sir, maybe close the AC or higher temperature.
You want to make it
Higher temperature.
higher temperature?
Feeling cold.
You're feeling a little chilly. Okay, excellent. You're having excellent. Feeling sorry for Sammy, who's turning pale and developing shock symptoms as we know. She's all right. You're all right? Okay, we'll turn the AC. What do you say? Turn it down, meaning turn it up. Okay. Make the temperature higher.
That's a better way. He's not used to AC.
All right. The only problem is that fan never shuts off. It's always on. Okay. I want to talk about something called incandescence and fluorescence. All right? Look up the word incandescence and fluorescence right now in your computers. Look up the words incandescence and fluorescence. Mr. Mohammed, where is your computer today? It's out in the hallway. Excellent. Professor Amir, where's your computer?
From my notebook.
I understand. Okay. So look up the words incandescence and fluorescence. And as you're looking that up, I'll draw something on the board and talk to you. Okay? There are two kinds of bulbs. There are those are horrible looking bulbs. All right, fine. They're terrible bulbs. If you look carefully, let's not look carefully. Let's call this is a fluorescent bulb. How do you spell? Do you know how to spell fluorescence? F-L-O-O-U. Excellent. Like flower, fluorescence, French for flower. F-L-U. Is that right?
No.
Florence.
Florence.
O-R-E.
Floor.
E-S.
Scent.
C-E-N-T.
S-C-S-H-E.
R-E-S.
Yeah.
So S-C.
C.
C-E-N-T. That's what I said.
Oh,
So I said I take you to that.
Scent. Scent has an S to it.
No, it's second.
Fluorescence. Is that right?
Yes.
You sure?
So like fluorescent light. So like fluorescent lighting, right?
Yeah.
Yeah, there's a T.
Well, I want to talk about the concept of fluorescence. Is that spelled correctly?
Yeah, it is.
That's what fluorescence. Fluorescence.
Is that spelled correctly?
Yes, it is.
Fluorescence, big
Yeah,
word.
it's emission of light by substance that has absorbed light.
Okay.
That's the definition.
All right. We'll get that definition when Amir is finished. He seems to have the floor by mandate of some sort. Are you through? Excellent. Let's get the spelling first, and then we're going to go to you for the first definition. What's the spelling of incandescence?
I-W-X.
I-N-C-A-C-A-N-D-E-S-C-E-N-C-E.
Did I ask you how fast you can spell it?
D-E-S-C.
D-E.
S-C-E-N-C-E.
Yes.
Incandescence. Okay. Let's go to the book. Let's see what the book says first. Sammy, do you have incandescence there?
Yeah.
What do you got for incandescence?
The light bulb that emits light by heating the filament present in the bulb.
Oh, I like that. Can you say that again? I'll repeat what you're saying.
The incandescent
The
bulb
incandescent bulbs, for instance,
emit light
they emit light. To read light, a light bulb, light. So the incandescent bulb emits light
by heating the filament
by heating the filament
present in the bulb.
present in the bulb. So incandescence. What else? Anybody else got incandescence? Yes, Miss Hickey.
The emission of visible light by a body caused by its high temperature.
Yeah. Excellent. Excellent. Yours was good. Yours was good. Very good. Excellent. Primo. However, the finished product together, perfect together, okay? New Jersey. Now, so Ms. Hickey, what did you say?
The emission
The
of
emission of
visible light
visible light
by a body
by a body
caused by
its
high temperature.
its high temperature. I feel like I'm taking oath of office here. All right? So incandescence is you're going from heat, right? You're going from heat to light, right? Heat to light. Or we could say, what do we say? We could say infrared to visible. So on the electromagnetic radiation spectrum, which you've seen 1,000 times in your young science career, infrared to visible, correct? Okay? Infrared to visible. Now, that's heat to light. Now, fluorescence. Hit it.
It's the emission of light by a substance
that has absorbed light or other electromagnetic radiation.
It also occurs when molecules are excited to higher electronic states by energetic electrons.
Okay. All right. Anybody else? Fluorescence. Well, how do these fluorescent bulbs, how do they work? How do they work? Well, you have a fluorescent bulb. You have these electrons going through mercury vapor, and that mercury vapor, upon excitation, gives off ultraviolet radiation. Gives off ultraviolet radiation, and it hits this kind of white powder coating, yes, on the inside, and it gives off visible light. So these fluorescent bulbs are converting ultraviolet radiation to visible radiation. Ultraviolet to visible radiation. Clear? All right, now, so that's incandescence and fluorescence. Now, let's just review very quickly, because some of you might not. I don't want to assume things. If I have the electromagnetic radiation spectrum, what generally, just generally, don't go crazy here, what type of electromagnetic radiation has the longest wavelength? Anybody know offhand? Anybody?
So can you
Anybody?
give us an example?
Would you like me to Google this?
Yeah, you could Google it. Yeah, put that in your Google, you know. Don't ask a question, because then you'll get all of these weird sites, but say electromagnetic radiation with the longest wavelength, for instance. You can say that. Yeah, just generally.
Radio waves.
Yeah! There you go, girl. Radio waves. Radio waves. And then what's next after radio waves?
Sound.
Somebody said sound. Sound is not electromagnetic radiation. Sound are mechanical waves that have very different characteristics. We'll talk about sound, but not right now. No, we're talking about light. This is all light. Electromagnetic radiation, another word for that is light. Okay? So what's next, do you think? What in general form? So radio waves would have the longest wavelength, and then what? No, heat's there, but not next. It's another long band.
Light.
It's all light.
Light waves.
What did you say?
Light waves.
I waves?
Light waves.
Anybody?
Well,
I don't know. Where they're going, but there's like X-rays.
This is a long band here. This is microwaves. Greek letter mu, microwaves. Those are the next, in general. Very long bands. Yeah? And then what? Then what do we got? Then we've got infrared, heat. Then it gets shorter, 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 okay? And then we have a very small band there, a very small band of wavelengths. Visible, very small, of all the bands of light waves. Visible is very small. And invisible you have red, orange, yellow, blue, green, indigo, violet. We'll talk about those as well. And then you have,
Like Roy G. Biv?
well, not like Roy G. Biv, exactly Roy G. Biv. And then you have ultraviolet. You have different types of ultraviolet waves, A, B, and C. You have X-rays, and then gamma rays. And this is called electromagnetic radiation. And just very briefly, does anybody know where it comes from?
What?
Does anybody know where electromagnetic radiation comes from? Well, if I have electrons orbit the nucleus, and they're going to, the electrons will be excited by some kind of energy, and then, so it'll absorb energy, and then it'll go quanta of energy. This is plural. Quantum singular. And this is electromagnetic radiation. So it really comes from, electromagnetic radiation comes from electron transitions.
So every time they make a quantum leap,
Yes, you get that quantum of energy, that's light. That's where light comes from. It comes from electron
and then that's
transitions.
when the colors are emitted.
Exactly. Yes, correct. Now remember, it's a very small number of those emissions. I'm going to try to set up a flame test, a chemical experiment for us to do. We're going to do a little chemistry in here. And we're going to do the flame test. I'm going to show you this excitation and how the actual colors are emitted. Clear? Okay. So that's it. Let's talk about these waves for a second. Low energy, right? Low energy. Yes? Low energy, long wavelength, right? Large wavelength. Low energy, long wavelength, right? Very small frequency. What's the speed of all this light? What's the speed of all this light? We talked about it in a past video.
Three times.
300 million meters per second, 1 second. 300 million meters, 286,000 miles in 1 second. Pretty amazing, isn't it? Is there anyone absent today? Can you look around? No? Are we all here? All right. I got like 5 minutes. I want to take the last 10 minutes to show you where some of the resources are. Now, radio waves. Let me tell you a story. I used to live in New Jersey, taught at a high school in New Jersey, and near Princeton, somehow cooperatively with Princeton, there was a fusion reactor called a tokamak. That was the general shape. It was a Russian design. Excuse me. Tokamak fusion reactor. And let me see if I'm putting this on the internet, so let me just say the memory's not what it used to be. So, a bunch of us teachers went out one time to a seminar. And the seminar was, we heard a lecture about the tokamak fusion reactor. And then we saw it. And the fusion reactor was like a giant donut. It took up a giant room. And inside this circular chamber was where the fusion took place. Now, I'm not going to teach you about fusion reactors. I'm just going to tell you a few things. That the fusion environment is 300 million degrees-ish. That's pretty hot. So how do they prevent it from burning down the room? Well, a magnetic field, believe it or not. I know, it sounds like something out of Star Trek. So how did they get it at 300 million degrees? How did they do that? You know, what they do, have like a giant burner underneath? Or how did they do that? Well, what they did was they generated radio waves and radio waves. Radio waves. Pretty amazing, huh? Radio waves. So let's say this is a radio wave. The radio wave has, these are nodes, okay? These are nodes where the wave changes direction. It's going to go this way, okay? Crosses the axis, if you want to say the x-axis. In trigonometry, if you want to say, those are nodes, yes? This is lambda, Greek letter. That's wavelength. Okay? How many wavelengths pass a certain point per second? It's frequency. Some books will call it F instead of nu, the Greek letter nu. This distance here, amplitude.
Yes.
Amplitude. How loud the sound would be the amplitude. Okay? Amplitude. For light, though, amplitude is vertical, yes? Okay? What I would do is I would add these light. I would add radio waves together in phase. So if I take another one and add it to this, I'm going to get this. So if I take a lot of radio waves and I add them together in phase, they add. And the amplitude becomes larger and larger, doesn't it? Yes? So this amplitude, that amplitude is going to be much bigger. Look up amplitude. Is amplitude from the level of the node to the crest? These are crests. Crests. Trough. Crests. Trough. Is the amplitude between the crest and the trough? Or between the node and the crest? Look that up. See what that is. This is called wave mechanics, where we're looking at the structure of the wave. So that's how they did it. They simply took, when I say phase, meaning you line it up, we're going to look at sound. We're going to look at destructive and constructive interference. And I'm going to end on this note. Are you ready? If I have the light, at the same phase, like that, they're in phase, right? I get this. I get that. It constructs. Becomes larger and larger. So you can use radio waves to heat the environment. $1 million a month was the electric bill to produce those radio waves to heat the inside of the chamber to 300 million degrees Celsius. Unbelievable. We're off.
You should come up with like a